Is going to be by Dr. Catherine Grier. She's a postdoc at Penn State, and she is going to be telling us about supermassive black holes and quasars. All right, so here's Karen.
All right. Okay, hello everybody. My name is Kate Grier, and today I'm going to be talking to you guys about some of the most massive and powerful objects that we have observed in our universe. So I'm going to dive right in here. So to start off, I actually want to give a quick background on black holes. And to understand black holes, we actually need to start off with the concept of escape velocity. Okay, so a lot of you guys have seen videos or just news about shooting rockets off of the Earth out into space. In order to get those rockets off of the Earth, we need to get them moving pretty quickly. And how fast those rockets need to move in order to escape the pull of the Earth's gravity is called the escape velocity. Okay, so how fast you need to get something to move in order to escape the gravitational pull. So if you shoot something off of the Earth and it's going too slow, it will fall back down onto the Earth. You keep speeding it up. Eventually, you reach the escape velocity, which will put it into orbit around the Earth. And anything faster than that escape velocity will shoot it off into space. And so escape velocity is an important concept when you're thinking about black holes, because the very definition of a black hole is an object that is so dense that there exists a point in space or a region in space where the escape velocity from this object is faster than the speed of light. So the idea is that we have our mass. Okay, you shove a whole bunch of stuff into a really small area, and there's a distance from that mass, that stuff, where the escape velocity is faster than the speed of light. And so anything that goes within that region, okay, that distance away from the object is called the event horizon, and that's where the escape velocity equals the speed of light. And anything that goes beyond that event horizon cannot escape, because nothing we know of can move faster than light, and so light itself cannot make it out. So this is the only equation that I'm going to show. And the reason why I'm showing this is just to give you an idea of what you have to do to get an object to become a black hole. So this equation here shows that the escape velocity has to do with the mass of the object, which is this m, and the radius of the object, which is r. Okay, and g is a constant, so we can ignore that for now. So basically, if you make something more massive, okay, you need a larger escape velocity. And if you make something smaller, you need a larger escape velocity from its surface. And so, so basically, just to get a black hole, you take a whole lot of mass and you squash it down and make it as dense as possible. So here's a couple of example escape velocities. So in order to get something off of the Earth, we have to have it go 11.2 kilometers per second, which is on the order of 25,000 miles per hour, for those of you who don't think in kilometers per second. And for different objects like the sun, which has a higher escape velocity, we go all the way down to a black hole where the escape velocity is equal to the speed of light by definition. So one might wonder, well, how big is a black hole then? How big does something have to be for you to have this region or this distance from it where you have where the escape velocity is equal to the speed of light? It depends on how much mass you have. So if we were looking at something that has a mass that's 3 times the mass of the sun, okay, then the event horizon for that kind of object is on the order of a small city in size. But you continue to add mass, you have a bigger black hole, that'll have a bigger event horizon. For example, if you wanted to make the Earth into a black hole, what we would have to do is to crush the Earth down to the size of about a small marble, about 9 millimeters in size. And if we kept all of the mass in the Earth and shrank it down that small, it would become a black hole. However, this brings me to one of the major myths in astronomy. Okay, black holes kind of have a bad reputation. They have this reputation that they're going to suck everything in. Okay, everything at some point is just going to be sucked into a black hole. But the truth is that actually black holes only act strangely when you get close enough to them. When you're far enough away, they actually act like any other thing that has mass. So, for example, the sun. If we were to shrink the sun down to about the size of a golf ball, it would become a black hole. But at the distance that we currently are from the sun, with the same amount of mass in there, we would actually continue to orbit the sun, the black hole sun, in the same way that we are currently orbiting. Now, it would cause other problems because we would no longer be receiving light from it, and that's very important to us. But we would not be, nothing would happen as far as the Earth falling into the black hole, for example. And so there are black holes scattered throughout space, and generally, as long as you stay far enough away from them, they are no cause for concern. So I feel like black holes kind of get this bad reputation that they're just harbingers of doom, but really just keep your distance and everything's pretty fun. So there's a few different kinds of black holes. One might wonder how we actually observe these black holes. Okay, I'm telling you that light can't escape them, which means that we can't actually receive light. So everything in astronomy is observed by the light that's coming from it. Okay, but we don't get any light from black holes, but what we do is we get light from things that are nearby or interacting with the black holes. So we have these types of black holes called stellar mass black holes. Okay, these are black holes that are on the order of a few solar masses in mass, and they are formed when massive stars die. So if you have a star that's on the order of 20 times the mass of the sun, or larger, we think that those stars, when they run out of fuel, they collapse into a black hole. And if they happen to be nearby to another star, so a lot of stars, most stars in the universe actually are in binary systems. They have other stars nearby. So if one of those stars collapses into a black hole and the other star gets too close to it, oops, oh goodness, what did I just do? Press the button here. There we go. The other star gets too close to it, like this companion star here, the black hole can start to pull material off of the nearby star, and that material spirals in around the black hole and eventually falls onto it. And when it's spiraling in, it gets really, really hot and becomes very, very bright. And so these stellar mass black holes, for example, are emitters of X-rays. And so we can actually observe them by the X-rays that are produced in this disk. We call it an accretion disk, material being accreted or falling onto the black hole. So these are stellar mass black holes. And one of the most famous stellar mass black holes is in the constellation Cygnus, a well-known constellation. And it's called Cygnus X1. Okay, X1 has to do with the X-rays. Okay, it's been observed in the X-rays, and it's one of the first black holes that they're really sure about that people were to observe. But now let's move on to supermassive black holes, which is actually the focus of my research. I sort of ignore the stellar mass black holes. They're too small for me. So supermassive black holes have masses on the order of hundreds of thousands to millions or even billions of solar masses. They exist at the center of all massive galaxies, and they are the powerhouses behind objects called active galactic nuclei, or quasars, which I will come back to in a minute. So these two images here actually show, this is a real image of the galaxy that hosts the largest black hole that has ever been found. And that black hole is 21 billion solar masses in mass. So imagine taking 21 billion suns and squashing them down to something about the size of Mercury's orbit, within Mercury's orbit in our own solar system. All right, so that's a lot of mass in a very, very small region. That's sort of what we have going here. And this is actually a simulation of what a supermassive black hole might look like from the movie Interstellar. Has anybody seen Interstellar? Got quite a few. Okay. They do some really spectacular simulations of supermassive black holes in Interstellar, so I highly recommend it. These types of images that they use are actually created in real, as physically accurate as they can simulations. So they're pretty neat to see. Now, to make a supermassive black hole, okay, we don't have stars that are big enough to explode and have 21 billion solar masses in them. So one of the ways that you can create a black hole is by merging smaller black holes together. So I'm going to play this little video real quick here. And this is just a simulation of two black holes that are getting kind of close together. And you can see they're sort of warping the view that we have around them. Black holes close in cause what we call gravitational lensing, where they sort of warp the light that's coming in around them. And as these black holes spiral in closer to each other, they eventually merge into one larger black hole. And so throughout the age of the universe, throughout the history of the universe, black holes have merged together, and eventually we've ended up with these galaxies that have billions of solar masses in them. So the Milky Way has its own supermassive black hole. It is called Sagittarius A star because it's located in the constellation Sagittarius. And this image here actually shows an infrared and an X-ray image on top of an optical image. And this is the very center of our galaxy. So at the very center of the Milky Way, we have a supermassive black hole that's about 4 billion solar masses. And the cool thing about our black hole is that because we live in the Milky Way, we're actually close enough to it, to this supermassive black hole, that we can actually watch the motion of things that venture too close in near the black hole. And we can actually watch the motion of stars and gas as they interact with it. This zoom in here, excuse me, is actually an X-ray image. Excuse me, I'm actually going to grab my drink for you real quick. An X-ray image that is produced when material is falling into the black hole. You get these disks of material. So actually, what I'm going to show you now is a little video that shows the stars that are very close in at the center of our galaxy. This is an infrared image. They took a telescope and pointed it at the center of our galaxy. And over a decade or so, they were able to observe the motion of individual stars. And this is where the supermassive black hole is. You can see there's not any light coming from that region. But you can watch, excuse me, as we zoom in, you can watch the stars appear to kind of bend around or zip around this region in space where we don't have any emission coming from this. And so that's where the supermassive black hole is. And if you have a look at all of the orbits of these stars at the center, this is just an image that shows the orbital paths of a whole bunch of different stars that are in toward the center of our galaxy. You can see, sorry, you can see that they all sort of swing around this place, and that's where and if you calculate the parameters needed to make those orbits, you end up figuring out how much mass is in there, and you know how big that region is just by the size of the telescope, and the only thing that could be in there is a supermassive black hole. So we see it in our own Milky Way. The Milky Way black hole is not doing a whole lot. There's not a lot falling into it at any given time, though we do occasionally see clouds of gas that fall in. And they actually can watch these clouds of gas as they get ripped up and fall into the black hole. It's kind of neat. But we actually see evidence for supermassive black holes in other galaxies. We don't have the ability to look at individual stars in other galaxies like we do our own. So what we do is we actually look at large populations of stars. So in a galaxy like this, for example, this image, we would look at the motion of sort of a whole lot of stars or a whole lot of gas in the center. And you can use the motion of those stars and gas to deduce how much mass is in there. And in the same way, once we use the motion of the stars and gas to figure out how much mass is in there, the only thing that can be in there is a black hole. But the black hole is very, very small in physical size compared to the whole rest of the galaxy, which is why it doesn't look like there's a hole in there. And so we see that actually pretty much every other galaxy has a supermassive black hole at its center. And this is actually, my job is to actually measure the masses of these supermassive black holes, figure out how much mass is in there. So why does one care about these supermassive black holes? Why am I spending the last decade of my life measuring the masses of these supermassive black holes? The answer is that we think that they have something to do with the way that galaxies evolve. Okay, pretty much every galaxy has a supermassive black hole, and they seem to affect the way that the galaxies grow. So that's one reason. And another reason is that supermassive black holes are actually the power mechanism behind active galactic nuclei, or quasars. So quasars and active galactic nuclei, I'm going to use these two terms pretty much interchangeably because they're basically the same thing. Are objects, so it started off, actually, the word quasar comes from the idea of a quasi-stellar radio source or a quasi-stellar object, because when they were first observed, they saw something like this that looks kind of like a star at first glance, but if you look at the color of that star, you see that it does not look like a normal star. It has very different colors than normal stars do. And so they called it quasi-stellar because it's a point. It doesn't look like it's like an extended galaxy like this over here. It looks like a point, but it also doesn't look like a star. And so they got the name quasi-stellar. And in some cases, they have radio emission associated with them. And so they got the name quasar. But what we are actually looking at when you're seeing this point here is you're actually just seeing the very, very bright center of a galaxy. Okay, so you're seeing the very, very bright center that has a supermassive black hole that has a lot of material falling into it. And that material gets very, very hot and it forms an accretion disk. Okay, we have this disk of material, and that disk gets really hot and really bright. And so bright that these are basically, we can see them across the entire observable universe. Okay, these are trillions of solar luminosities. We're looking at them. We can see them billions of light years away. They're extremely powerful. And what it is it's just light coming from this disk around a supermassive black hole. And so we call this an active galactic nucleus, or an active galaxy. So the Milky Way doesn't have a disk like this that's particularly bright, so we call it a quiescent galaxy. But we have these active galaxies as well, or quasars, that are actively accreting a lot of material. And so the way that you produce these accretion disks is basically just by having material that comes too close to the black hole. So here's a little video that shows a star as it is orbiting a black hole. This is just a little simulation here. And as it comes around and approaches the black hole a little bit closer, the tidal forces from the black hole shred the star apart, and it spirals in and creates a disk of material. And that material heats up, again, gets very, very hot, and we can see it from across the universe in some cases. And so sometimes, this phase in a galaxy's life can last a very, very long time. But it is actually thought to be, by many, to be a phase in the life of a galaxy when there's a lot of material that gets pushed in toward the center of the galaxy. The most distant known quasar that we know is 12.9 billion light years away. So, and this is an image of it. It's actually this tiny red dot here in the center, which is an infrared image, and it's probably kind of hard to see from far away. We can see quasars across the observable universe. This gives us a way to look at the universe when it was very young. Okay, so the light from this quasar was emitted only 770 million years after the Big Bang. So the light that we're seeing tells us what things looked like back then. So the next question is, what makes a galaxy turn into a quasar? If it's a stage in the life of a galaxy, what causes it to do that? We're not totally sure, but a lot of galaxies that are around quasars tend to look disturbed or sort of wonky shaped. And so we think that actually one way to produce an active galaxy is by colliding two galaxies or something similar. And when you collide two galaxies, I'm going to start this video too. Lost my mouse. So if you take two galaxies and watch them collide, so this is actually just the gas distribution in these two galaxies. And as they collide, a lot of material gets shoved toward the center. Both of these galaxies have their own individual supermassive black holes that will eventually merge together. You get these really cool effects along the way as the galaxies interact. And this is a simulation that was done But one of the things that comes out of it is you can see the centers of both of these galaxies now are starting to look really bright compared to the rest of the galaxy, because as these galaxies passed each other, the gas got shoved into the center, which is now feeding the black hole and creating a quasar. And sometimes the material also gets blown out. Quasars can actually shoot material out of galaxies as well. So there's a whole lot going on there, but that's one way that we think that active galaxies are actually created. And one example of just how much energy and power is coming out of these things, I think this image actually demonstrates this beautifully. We actually see these giant jets, or radio, we call them lobes, of material that are being shot out of galaxies sometimes. So this image actually shows the visible light in the background, and then the pink is actually radio emission. And if you were looking at this without the radio emission, this galaxy would look about this size. Okay, it would look pretty small, but the active nucleus in this galaxy is generating so much energy that it's funneling material out way beyond the extent of the galaxy itself. And so it's really a pretty stunning effect. So these objects, quasars and active galaxies, are really the most powerful and I think pretty cool things that are out there. And because they're so bright, we can use them to learn a lot about the universe at bigger distances than we would if we were looking at normal galaxies. So I will end there. Thank you very much.
So we do have time for questions. If anybody has any questions, ask Kate.
Inside event horizon, is a black hole an event?
So the question is, inside the event horizon, is a black hole two-dimensional? I want to say the answer to that is no, but we actually have no real good idea about what's going on inside the event horizon. Our knowledge of physics breaks down once we go past the event horizon. In order to fully describe what's happening in there, we need to know something called quantum gravity, and we don't have a way to explain it. So, and unfortunately, by definition, we actually can't really get any information out from in there. So the idea is that material that goes in there just falls into an infinitely small point called a singularity, and that's, there's a lot of people who actually think pretty deeply about that, probably a lot more than I have. So they might be able to give you...
I haven't heard anything about that, just curious.
Right, yeah, so as far as we know.
Matthew McConaughey did it Interstellar.
That's true, Matthew McConaughey did travel into one in Interstellar. We do think that there's some problems with that. So yeah.
That very distant quasar. You said 700 million years after maybe the Big Bang or inflation or whatever. Doesn't that seem like a really short amount of time to actually form a quasar of that magnitude? I mean, your graphics spanned way over 1 billion years, where the two galaxies were dancing with each other. So we're talking about just 700 million years after the Big Bang, and you've got something that already looks like it's developed in an old universe.
Right. So the question is, this quasar that we have that's 12.9 billion light years away. Very soon, we're observing it very soon after the Big Bang. How has there been time? That seems like a very short amount of time to build a quasar of such strength. And that is actually true. There is a major issue in galaxy evolution studies in producing such large black holes in such a short period of time. People are actually having a very hard time accounting for it. That's sort of one very active area of research. It is true that back then the universe was much smaller, and so things were closer together, and so there was a lot of possibly more interaction between galaxies that had managed to form by then, just because space was smaller. But that is actually a problem, and there haven't been, to my knowledge, very satisfactory answers to it yet. It may be that these answers exist and I haven't heard of them yet, but as far as I know, that is a problem.
problem.
Yeah.
I have a question. Back in one of your original slides, you had a black hole, 90 degrees to your accretion history, has a jet coming out, perpendicular to it. Several questions. One, what's the jet composed of? Two, why is it at 90 degrees? And three, if it's a black hole, by definition, it can emit radiation because the rate at which your escape velocity would have to exceed the speed of light. So what is the jet at 90 degrees?
So the question is, I showed you some, especially at the end, even in this image actually, you can see these jets coming out that at a 90-degree angle from the accretion disk. So the question is, what are those jets, and how do you produce those jets? Because if nothing can come out of the black hole, then how do we get material coming out? So the answer is, these jets are thought to, and also why 90 degrees? So these jets are thought to be produced by black holes can spin. So black holes are spinning often, and they also, a lot of the material close into the black hole has very strong magnetic fields. And when the black hole's spinning, it can actually drag and move around magnetic field lines. And what happens is this, because there's so much energy involved, this dragging of magnetic fields can actually accelerate particles like electrons to really high speeds. And so what you're actually seeing is we call them relativistic because they're approaching the speed of light. Material like electrons that just gets thrown out from near the black hole. It's not actually coming from within the event horizon. It is coming from very close in, but it's not actually coming from within the event horizon, and it gets funneled along these magnetic fields that get sort of warped and dragged along in these funnel shapes by the spinning black hole. And the reason why they are at 90 degrees, I don't know how to give a short answer to that. So it's at 90 degrees to the spin axis of the black hole. So the black hole's spinning, these jets will come out up and down, and that just has to do with the angular momentum of the system, the spin energy of the black hole. Did you have another?
Well, yeah, just following up on that. So, since the magnetic field can't be near the black hole, is it the red horizon that's creating the magnetic field, or is it much trade?
So the question is it the magnetic field that's creating the event horizon that's causing this magnetic field? It's actually the material that's being pulled in. So this disk of material. This disk often has multiple parts to it. So you have a disk, and you have like some winds coming off of the disk, and because there's so much going on in this region, there's a lot of material shoved up in a small region. It's actually the movement of that material. So it's not the event horizon itself, but because a lot of this material is moving so fast, as it gets closer to the black hole, the material starts moving faster and faster and faster. And you have these charged particles. When you have moving particles like electrons, they generate magnetic fields. So if you have charges that are like charged particles, that's what's causing this magnetic field. So.
Okay, I have one more follow-up.
Okay.
Okay, because I was just reading your paper that some of the speculative used to derive this information, this idea from quantum mechanics, from real relativity and string theory. So you can take which one with that. And he was saying that in specific spots in the accretion disk, the temperatures are near absolute zero, and the metals are actually forming superconducting streams or circles around in the accretion disk, and that's what is producing all the magnetic field.
I see. Okay, so you read something about metals creating superconducting streams that cause these magnetic fields. I'm not actually sure about that, to be honest, offhand. I would have to have a look at whatever this is.
Hasn't done anything else.
But yeah. So, any other? Are we out? Okay.
Let's thank Kate one more time.
Thank you.